All right, let's dive right in. Today, we're going deep into the V-engine codebase. We're moving past all the theory and looking at how the architecture actually works in the real world with the real code. So in our last explainer, we talked a lot about the why behind the engine's design, right? We covered those big ideas, like specification-driven development, having a unified system lifecycle, and why a deterministic update pipeline is so important. Well, today, we're finding the receipts. We're going to trace that philosophy straight through the C++ source code, and I'm going to show you how those architectural goals aren't just suggestions, they are hard-coded rules that the engine actually enforces. This right here, this is our whole journey for today. We're going to follow what happens in just a single frame. From the second the engine starts up with initialize, through its main run loop, and all the way to a clean shutdown. And we're going to see it all inside the actual repository. So here's our roadmap. We'll kick things off by connecting the theory to the code. Then we'll get into the boot sequence, the per-frame cleep line, and even end-of-frame cleanup. We'll also look at how you can add your own system safely, and finally, we'll tie it all back to prove those core principles we've been talking about. Okay, so let's start where any developer using this engine would, the public API. This is really the front door to everything the V-engine does. And here it is, pulled straight from engine.hpp. The main engine class has this really small, very deliberate API. You've got initialize, run, update, and shutdown. That's basically it. And this minimalist design is totally intentional. The engine class itself doesn't do the complex stuff. Its main job is just to coordinate the application's lifecycle and then hand off all the heavy lifting to the system manager. So what actually happens when we call that initialize method? Well, that kicks off the boot sequence. And you'll see it's completely deterministic. It's designed to enforce dependencies from the very first line of code. The engine follows these exact steps every single time. No exceptions. First, it parses any command line arguments. Then, boom, it immediately hands off control to the system manager to get all the systems online in the right order. After that, it applies settings from external config files, in this case, TOML files. And finally, it can run an optional setup function for any game-specific logic, like loading the first level. Now, this is super important, and it's a key to the engine's stability. The system manager makes a crucial distinction between registration and initialization. Think of registration as just building a catalog, a list of every system that could possibly exist. Initialization, on the other hand, is the separate, carefully ordered process of actually turning them on and making sure their dependencies are met. Keeping these two things separate prevents so many potential headaches. And you can see that registration process right here in systemmanager.cpp. This function, register core systems, it's really just a big explicit list of calls to add system. This creates that complete catalog of every core system, from the config system all the way to the render system. It's simple, it's readable, and you can audit it. There's no hidden magic going on. And this quote just perfectly illustrates one of those core principles we talked about. This idea of externalized configuration isn't some nice-to-have feature. It's not a slogan. It's a hard dependency that's baked right into the engine's boot order. You can see the proof right here in the code. Inside initialize systems in order, look what comes first, the config system. It's one of the very first things to get initialized, and it immediately loads all the TOM configuration files before critical systems like the platform system or timing system even start. This guarantees that when those systems wake up, their settings are already loaded and ready to go. Okay, so after configuration, the entire engine's initialization pivots around this single moment, the creation of the ECS registry. This ent.registry is basically the central database for our game world, and once it exists, it is explicitly injected into every single system that needs to touch the game world. This means no global singletons, just clear, centralized dependency injection. All right, let's fast forward to the run loop and see how this all comes together in the per-frame update. Once everything's initialized, the engine enters its main loop, and just like with booting up, order is everything. This right here, this is the heart of the engine's determinism, pulled directly from update frame-based systems. Every single frame, systems get updated in this exact order. You can see platform system and input system go first, so we always have the latest player input. Then come the simulation systems like AI and physics to update the world state, and only after all of that is done do we run the render system. This strict order prevents all sorts of bugs, like rendering an object where it used to be a frame ago. So after all the main updates are finished, there are a few final tasks that are intentionally pushed to the very end of the frame, all for the sake of consistency. Inside the engine run loop, you can see these explicit end-of-frame hooks. The input system finalizes its state for the next frame, the event system dispatches any events that were queued up, and so on. Deferring these things ensures they happen at a predictable point and don't mess with the main update logic. You don't want an event firing halfway through the physics simulation and corrupting its state. So, with all this explicit ordering, you might be thinking, how on earth do I add my own system into this thing without breaking everything? Well, the good news is the engine is designed to make this a really safe and predictable process. Extending the engine is designed to be boring. And believe me, that's a good thing. You just follow a simple checklist across a few key files. You declare your system, you register it, you wire up its dependencies, you pick its exact spot in the update order, and then you define its shutdown behavior. There's no hidden magic, which means no hidden surprises down the line. Okay, so we've traced the code from the very first call to initialize all the way through a single frame update. Now let's connect everything we just saw directly back to those big, high-level architectural principles that we started with. So here's the crucial takeaway. Every one of those architectural principles isn't just some abstract goal. It has a concrete receipt right there in the codebase that proves and enforces it. The unified lifecycle? That's enforced by the base system.hpp interface. Configuration as a dependency? Proven by those early load config file calls. And the deterministic pipeline? It's sitting right there in update frame-based systems. It is all explicit, and it's all auditable. Now, this strict, deterministic design gives you incredible stability. It makes debugging so much easier. But it is a trade-off. It absolutely prioritizes predictable order over something like runtime flexibility, being able to load plugins on the fly. And that leaves us with a final thought for you to consider for your own projects. When might that trade-off actually be the wrong choice? What kind of game might actually benefit from a more dynamic, less rigid architecture? It's a key question every engine architect has to answer.